So I've shown you that we can raise up viruses that will bind with high specificity to cancer-associated proteins. We now are working out ways to splice those viruses into electrical circuits. And let me show you some results in this. OK, so here's what we're trying to do. All right, so imagine that you have some gold electrode over here. Imagine now that we have some handle that we have to attach to the gold electrode. Turns out viruses don't just bind randomly to gold electrodes. So you actually have to set up little arms that will reach up and grab on to the viruses. So we set up a layer of the arms down here, and then we attach our viruses. And these are the skinny viruses that I showed you on a previous slide, the ones that look like long filaments. Those are the harmless viruses that we're using in this experiment. So we make this surface, we coat it with our viruses, and then what we want is we want something that upon binding to the cancer-associated protein or the analyte over here, we get some electrical signal. Okay, now here's what this actually looks like. And I'm actually showing you some microscopy that was done by Teresa McIntyre, who's in the audience today. And here's our harmless virus again. Hey, check it out. Here's the head again down here, that cluster of grapes. And that surface of the electrode that I showed you that has the arms sticking up looks like this. So it's fairly smooth. There's actually some interesting junctions over here in this black canyon. But in any case, after we add our viruses to the surface, there's this big pile of spaghetti. And Sudipta, can you see that in the back? Yeah. OK, so that big pile of spaghetti, those are the viruses that are attached to our circuits. So we've actually wired them in. And in the experiment that I'm going to show you today, we're actually working with macro scale electrodes. So we're actually working with electrodes that you can actually see that look like this. Okay, so they're actually quite large. So this is someone's hand over here. And I'll tell you towards the end how we're scaling this down quite a bit. OK, so we have our viruses that are attached to the electrode, and we've engineered the viruses to recognize specifically a cancer-associated protein. Now what happens when we put electricity through these circuits, and electricity passes through the viruses as they recognize their cancer-associated protein? OK, so it turns out there's actually quite a bit of complicated analytical chemistry, and I'm going to make it really straightforward. So we do a lot of experiments that look like this one here. This is a technique called impedance spectroscopy. What we're doing is we're looking at current going through a circuit as the current interacts with the viruses and interacts with what the viruses are binding to. And the kind of current we're using is alternating current. So there's two kinds of current. There's direct current and there's alternating current. Alternating current is what comes out of the walls. It comes out of the walls with a frequency of about 60 hertz. That's the sort of humming noise that you sometimes hear from electrical appliances. And let's just focus in then on just one panel. If I can just call your attention to panel D over here. Here's what a typical experiment looks like for us. Okay, so along the x-axis, this is the frequency of that alternating current. So the current has some oscillation associated with it. That oscillation has a frequency. That frequency is along the x-axis. Now, along the y-axis over here, this is signal to noise. Okay, and a higher number up here means bigger signal. Okay, so first, here's binding by something that we know in blue doesn't bind to our virus. And the signal to noise ratio is somewhere around 0. That's what we expect, okay? We call that a control, because we know in advance what the outcome of the experiments is going to be. Signal to noise level of 0 for things that aren't supposed to bind to the virus. Now, when we add things that bind to the virus, and here's two things, one in red and one in green, we actually get pretty good signal to noise ratios of greater than 15 to 1, which are levels that we can actually detect quite readily using electrical circuits. Okay, 15 to 1 is something that I can actually wire in to some device that would then look for it. Okay, so here's binding in green by that cancer-associated protein, PSMA, and then here's binding by an antibody that's been raised to bind specifically to these viruses. Okay, so in either case, we're getting pretty good signal-to-noise ratios. We actually think we can make this a lot better, and that's what my laboratory here is currently doing. And I'll just give you a very, very preliminary glimpse of this. One thing that we're doing is we're massively scaling down the scale, the size of these electrical circuits. Doing this actually tremendously improves sensitivity. Okay, so we can actually improve sensitivity greater than tenfold because there's this interesting surface to volume ratio increase as you get down to little tiny nanometer scale circuits. Things actually get a lot more sensitive because there's a lot more surface that's exposed in those tiny little size regimes. And this is something that's now ongoing in the Penner laboratory. In my own laboratory, led by people who I see in the audience today, we're actually developing ways to make much more sensitive viruses, viruses that bind with much higher affinity. And very preliminarily, I saw some data yesterday that suggested we've improved things by around a factor of 20,000, which is a really big deal, and I'm very excited about it.